climatic extremes in Mediterranean climatic regions. Now, Ricardo Trigo graduated from physics, got a master in geophysics, and a PhD in climatology from the Climatic Research Unit of the University of East Anglia at Norwich. Now, the Climatic Research Unit, CRU, is a famous center in climatology that maintains datasets, the CRU datasets, which are the basis of countless climatic analyses carried out around the world. Ricardo Trigo is an associate professor here at the Faculty of Sciences of the University of Lisbon, and also he is director of the Don Luis Institute. His main research activity has been focused on the impacts of different types of weather-driven natural hazards, with particular emphasis on floods, droughts, heat waves, and wildfires, and particularly how these phenomena are related to specific atmospheric circulation patterns, such as the North Atlantic Oscillation, blocking highs, or atmospheric rivers. He has published extensively, often in collaboration with colleagues from different disciplines, and in 2008, he was awarded with the International Journal of Climatology Prize of the Royal Meteorological Society, UK. Please, Professor Trigo, the floor is yours for 50 minutes.
Well, thank you very much for the introduction, and thank you for the organizers for inviting me. It's always dangerous for a group of ecology people to invite a physicist, but that's the danger you have to stick with. So, I'm going to show at the beginning some graphics that I'm sure most of you have seen published in IPCC or other reports, such as this type of changes in average surface temperature at the end of the 21st century, associated with either a very steep increment in greenhouse gases with the RCP 8.5 or not so much, but probably the way the world is evolving, we are closer to this situation in the future than to this one. But in any case, what I would like to emphasize is that you can see an increment in temperature that is larger over the continent than over the ocean. Second, it's much larger over the northern and southern pole than in the tropics. And third, you can see that the signal is coherent throughout the world, so it's the same signal. But if we move to precipitation, you don't see such a coherent signal throughout the world. Independent, if we're in the weak or strong climate change scenario, what you can see is a difference between areas where you have an increment of precipitation in high latitudes and in the equator, and at the same time, areas where you see a decline of precipitation, okay? So this, from the hydrological cycle perspective, it's extremely important. Now, if we stick with the precipitation and hydrological variables, such as precipitation, evaporation, and going to something that is extremely important for ecosystems, runoff, soil moisture, and if we maintain in the higher end of the climate change scenario, what you can see is that this imbalance between precipitation and evaporation means that there are particular areas of the world that I've highlighted here, and that show this imbalance in a particularly striking way. And those are mostly what we consider Mediterranean climate regions. So that encloses the entire Mediterranean, most of southwest states, the Chile coast, the South Africa, and parts of Australia. This is very important, and if you are aware of, in the just last decade, we've seen major drought situations in all of these areas. If you remember 2016 and 17, water was running absent of Cape Town city. In São Paulo and Chile, there's been mega drought situations. In California, I will show you 5-6 years of continuous drought. And of course, I will show most of the work I've been doing in the Mediterranean. But all of these have seen extreme drought situations, either during 1, 2, or 3, 5 years, with enormous human and ecological impacts. Now, one of the main problems here is that besides this direct impact in droughts, you have a secondary impact, which is heat waves. Heat waves nowadays, and I've been studying them for 2 decades, are to a certain extent also consequence of the dryness of these areas. And heat waves together with drying trends imply in most of these areas something that is very important for you, which is fires. Fires are driven by these compounded events of dryness and heat waves that act together. And I will show briefly some of these examples. We had an extreme drought situation in Iberia in 2004 and 2005, and by extreme I mean the most extreme one in most of the areas south of this red color, and in Lisbon for 150 years, and in Madrid as well. So obviously we had quite a large amount of impacts in agriculture, in ecosystems, in hydroelectricity production, okay? As an example, let me show you something that we've published at the time, which represents this very simplified index of vegetation activity that you know, NDVI. And what the colors are showing is the number of months with consecutive negative NDVI anomalies. So this means that all these areas that I've shown you with less than 50% of precipitation during that hydrological year show a large number of months with negative vegetation activity. And 2 years afterwards, a major drought started in the other side of the Mediterranean basin, and we called it this fertile crescent. And at the time, we thought it was a 2-year drought, because after 2 years, using the same color bar, you can see the area that I'm depicting goes from the southern Iraq all the way to Lebanon, enclosing most of Syria, Iraq, and southern Turkey. And you can see by color that you have extremely low precipitation in 2008, 2009. We then realized that 10 years before there was also a similar large drought. So when we pick up all the precipitation for that area, what we can see is that the 2 most intense drought episodes of 2 years occur precisely in the last decade, that is 98-2000, 2007-2009. But apparently when we wrote this in 2010, we didn't realize that the drought was proceeding. So it was a going situation, and this had tremendous impact, as you might expect. Of course, using the same type of approach, we can see a number of months in all these areas, from Lebanon all the way to Iraq, with consecutive months with negative NDVI, both in 2008 and 2009. And more important, as I was saying, the drought didn't stop in 2009, and in fact, in 2010 there was already 1 million refugees inside Syria prior to the start of the war. So this is very important, and this has been studied in high-ranking papers such as this one and others in Nature and Science. We now know that part of the problem with the refugees coming out of the Middle East is due to climate change, okay? And this is extremely important for Europe. Now, in a very simple way, let me show you that the precipitation for Syria is declining, the number of droughts is increasing, but you must see that together with the increment in temperature. If you put those together, then the possibility of major droughts, such as measured by Palmer Drought Index, which is one of the typical drought indices, you see a larger tendency for major drought in recent years than just the one induced by lack of precipitation. This is important for Eastern Mediterranean, it's important for Iberia, it's important for California, it's important for all these semi-arid regions of the world. Droughts are occurring not only in this area, not only because precipitation is declining, but also because evaporation is increasing due to the rise of temperature. And when those two are combined, then the lack of water for plants is increasing. Of course, in this case, the problem was particularly acute due to the increment in population in Syria. And so it's very different to feed 25 million people than to feed 5 million as 50 years before. So this increment, again, compounded a major effect there. So just a few years ago, and to stress again, we were back into a major drought situation in Iberia, 2011 and 2012. Again, if we look into Iberia as a whole, what we can see using Climate Research Unit precipitation, what we can see is that the three major drought events, when we consider the entire Iberian Peninsula, were observed, were in fact the last three major events. So 98, 99, 2004, 2005, that I mentioned was the biggest one, 2011, 2012. And when we start to see this clustering of very large episodes at specific periods, we know that something is really happening here. This paper we've published with some colleagues from Oxford, and we use lots of dynamic models, lots of dynamic runs, not models, the model was just one, but models that we can run thousands of times using spare time of people's computers. And what they've shown is that we can only reproduce this increment in large droughts in Iberia if the dynamic models are run with the greenhouse gases emitted in the last century. If we don't use the real greenhouse gases emitted, then this increment in droughts over Iberia will not appear, okay? So this is a signal of something that is already happening, partially due to climate change, okay? This is very important. Of course, all these droughts had major impacts in agricultural production. This is an example of production of wheat and barley, where you can see that these two major droughts I mentioned, 2005 and 2012, you see a drop in the cereal production, both in Portugal and in Spain. And in fact, the 99 one I mentioned, you can see also here. So, what is the panorama over the entire Mediterranean basin? Well, that is shown here. If we pick precipitation within this red rectangle and we compute the evolution since the beginning of the 20th century, what you obtain for the precipitation inside this rectangle is this time series. And you can see, just looking at this plot, that there's a decline in the last few decades. So a number of teams in Europe and in the States run the most comprehensive models with both oceanic and atmospheric components. And again, and this is was run under this CEMIP project, which encloses lots of different models. And the only way to reproduce that type of decline of precipitation that you can see here, both in space and in time, was when those models were incorporating CO2 and greenhouse gases as we know they've been injected into the atmosphere in the last century. So when we run those models without incorporating CO2 and only with natural changes such as solar variability, volcanoes, and so on, we don't see this decline of precipitation in this area, okay? So this is very important because this again is stressing that what we're seeing in this type of Mediterranean areas is already to a certain extent the result of climate change, as models had predicted 20, 30 years ago. So when we see those climate change scenarios, we should put these in, we are already in the middle of something that is going on, okay? So that is always important. And picking up in some of the results by a review article led by Wolfgang Kramer, that is here, it is important to look at this also from the temperature perspective. Not only precipitation is declining, but temperature in the Mediterranean area is increasing faster than the global average. And according to models, that is going to be the reality in the coming decades. So there's this divergence between what is happening at the Mediterranean and at the global scale. And again, and I will show in the second part, that this increase is expected to be associated with more frequent heat waves. They've also shown in this quite nice graphic that each degree of warming implies on average less 4% of precipitation, and you can see that here in these, all these gray lines correspond to a different model, and the red line is the average of the models into the future when you compute increased temperature, and you can see that on average that implies a decreased precipitation, particularly in the southern Mediterranean. Right, so while all of this was happening in the Mediterranean, in California, we've seen in the last 2 decades 2 moderate droughts and a huge drought that is confined here to these 4 or 5 years. And in fact, the driest years ever in the last 120 years in California were observed here in 2013-14. And that really had major influence, particularly in the increment of fires and the collapse of agricultural production in some of the areas. You know that most of the agricultural production in United States is coming out of this valley here. And this is the difference of a satellite picture at the beginning of 2014 compared with the same day 1 year before. Unfortunately, there's some clouds here, but you can see that this is much greener all over than here. So in just 1 year, comparing the same day, you can see a huge drop in vegetation activity at the beginning of this year. And that continued for several years, okay? So these had major ecological impacts as well. Now, what is driving this tendency for dryness in California is quite similar to what is driving dryness in Iberia, and we'll see also in Southern Hemisphere. And what is that? In simple terms, without going into much detail, there's a tendency for storm tracks that usually cross here to pick up the jet stream and go northward, and you have a wetter area here in British Columbia and Canada, and much drier in California and part of the Rockies. And this tendency for the jet stream to wobble is also a signal of climate change. Why? Because as temperatures are increasing faster in the northern pole than in the tropics, the temperature gradient between the tropics and the pole is declining. And that temperature gradient is the one that maintains the westerlies at the fixed position and not going northward or southward too much. The more we weaken that temperature gradient, the easiest it is for the storm tracks and the associated jet stream to meander north and south. And that, what we're seeing here, is happening quite often also in Europe, okay? Of course, it's different if you're talking about winter and summer. I don't want to go into details, but basically this tendency to decline the temperature gradient has implications also in dynamics. Right, what about Chile? Well, Chile is the worst case. They are still in drought. It started 10 years ago. Most of the population in Chile, Santiago is here, is living in this central area. Of course, Chile starts here and ends, but most of the population is here. And this graphic shows the decline of precipitation. The zero line is here. It's showing precipitation for each latitude, for each year. And what you can see in this part where population really occupy the land, you can see this tendency for drier than average in 2010, 11, 12, and so on. So all these years, they had lower than average precipitation in Chile. And there's René Garreau is one of the guys really publishing a lot there. And of course, the impacts of these are immense. Just a few examples. While we have this rainfall deficit, and this is just for the first 5 years, you have less load of sediments going into rivers, and of course, less sediment reaching the sea. For example, compare the blue circles in 2008 in these rivers with 2013. There's a huge drop. There's a tendency for a vegetation change as depicted, I believe, by satellites in all this area. And of course, the amount of burn area, if you compare the average for this period with these 5 years, you see a huge increment in Chile. Again, think about increment of temperature together with the drop of precipitation that is inducing all these together. And from the dynamical point of view, it is more or less the same. So Garreau provided here the historical drought fingerprint. Chile is here. So this is the situation for typical droughts where we have a high crossing all the Pacific here and a low with the storm tracks going further south. During these 10-year mega droughts, what you see is this huge increment of pressure and geopotential height in all equatorial and subtropical latitudes, and much lower here. So storm tracks are really passing much to the south than in the usual situation. And this is compounded with sea surface temperatures much higher than during usual droughts. Here is the sea surface temperature anomaly during normal droughts. You see here some positive anomalies, but during these 10-year mega droughts, and of course, sea surface temperatures are increasing anyway. So some of these drivers are there almost on a permanent basis, okay? Right, so much for precipitation and dryness. What is really worrying us here in Europe in the last month is extreme temperatures, okay? We had 2 heat waves in the last month with record-breaking temperatures all over Western Europe. So what is happening in climatological terms? Well, based on this, that is already 8 years old, and this is danger in extreme analysis, you can see all summer northern hemisphere temperature distribution when you remove climatology. So each color here is presenting a 10-year distribution of anomalies for summer northern hemisphere continental stations, okay? So what you see is that during the 50s, 60s, 70s, nothing really important happened. But as we move along the last few decades, you see this tendency towards higher temperatures and particularly much higher extreme temperatures. It is not so much in winter. Of course, in the summer, this is particularly striking because besides the thermodynamical impact, you have the dryness of land that is also increasing this tendency, and you don't have that so much in winter. Now look and imagine the probability of a 3 degrees anomaly 50 years ago and now. And you must imagine that this purple curve is not the current climate. The current climate is somewhere here already, okay? And now compare the probability 50, 60 years ago of a 3 degree anomaly, which would be almost zero, virtually zero, and compare that with what is happening in the last decade. So we've moved from 0 to 5% to 10%, and in a few years it will be 30%, okay? This is important to put in perspective what I'm going to show in terms of major heat waves in the last few years. Of course, 2003 is a major event that is at the back of our mind. For example, and this is important, France, it's for some reason they closed schools last month. They were really afraid of a repetition of what happened 15 years ago. And 16 years ago, what happened there was an increment, a doubling of mortality in all these departments around Paris and the Loire Valley. So all this color means a duplication of mortality. And at the time when we look at absolute temperature, maximum temperature for those 15 days, these didn't match well the mortality increment. But of course, when we remove the climatology, that matches much better. And so people are used in their place to the typical distribution. Nowadays, that is very easy to accept. 2 decades ago, it was quite difficult. We had quite a few problems publishing in journals with medical doctors as reviewers, because they were not aware of this difference between 40 degrees impact in Lisbon, in Madrid, or in Paris. That's completely different. In Madrid, it doesn't kill that much. In Lisbon, it kills quite a lot. In Paris, it's a catastrophe. Okay, so it's quite different. So what happened during those 15 days? I'm showing this because, again, you can see this pattern that is similar to what I've shown you in California with the jet stream going up. Okay, but this is summer, and you must imagine that jet stream is going in this around Europe, and you have this intrusion of hot Saharan air coming out of Africa and going into Europe. And in fact, as I will show you later, this is precisely what happened in the last 2 major heat waves. Of course, if you compute the anomaly of temperature in the upper air, this matches pretty well where we've seen the higher levels of mortality. Right, and what about Portugal? You know that Portugal, we have quite a lot of fires. In usual years, it can burn up to 200,000 hectares, but in extreme years such as 2003 and 2005, that was out of scale. 2003, we had more than 5% of the territory burning during the summer. And if you see the colors that correspond to satellite passages, you see that most of it is in red, and red means between 2 of August until 14 of August. So all this reddish area was burned during those 2 weeks, while a lot of people were in Europe, up to 60,000 extra deaths occurred due to this heat wave during these weeks. Right, just a few years afterward, we had another important heat wave in central Mediterranean, and the reason I'm showing this is that it really burned quite different landscapes and land covers, and also to show you that heat waves in Greece or Turkey are related with atmospheric circulation anomalies that are totally different from what is happening in Iberia or France. So you see here an intrusion of hot air coming out of Russia. This is important in terms of what is happening in Western and Eastern Mediterranean. It's very rare to have heat waves occurring at the same time, and even during the same summer, in Iberia and Eastern and Central Mediterranean. And the reason for this mismatch is this one. The dynamical mechanisms to produce this type of heat waves are different. This is important when you're responsible for managing airplanes and information at the European level, because you can help countries separately, and you don't need airplanes to go and help Portugal, Spain, southern France, Greece, Croatia, all together at the same time, because usually those huge heat waves will not occur simultaneously in those different places. Right, and afterwards we had the mother of all heat waves up to now, which is this Russian Black Sea heat wave. This is already a bit outside the Mediterranean area, but this was so big, and this is the type of things that we must prepare into the near future, not the long future, that we should study them and be aware of what happened. So in 2010, in August, we had a heat wave that broke all records. So the colors are showing temperature anomalies. All the dots are showing record temperatures compared with the previous 110 years. So a huge period of comparison. And what you see in these ISO lines is the anomaly in standard deviations. So 3 standard deviations is huge. 4 standard deviations is amazingly huge, okay? So 4 standard deviation, and you see these records at the week, 2 weeks, 1 month, and the seasonal time scale. So we picked up all the information we had for a long time in the European window, and I mean really long time. This means to merge data from NASA together with the multi-proxy data that uses old observed data. Fortunately, in Europe, we have observed data since late 17th century, just in a few stations, lots of data in 19th century, but we have proxy data that enables us to produce quite robust reconstructions. And if you use all that data, what you see is that the coldest years are represented here, the warmest years are represented here, and you can see 2007, 6, 2002, 2003 that I mentioned before, and 2010 that is here. And you can see that these two are completely outside the normal distribution curve that is typical of 500 years of data, okay? And I will show you that just the last 10 years since this happened, it's still going up to the right, okay? In fact, we can see that these huge heat wave, or these 3 that I mentioned, 2003, 7, and 10, change the panorama of heat waves and the way we see the warmest summers in Europe. If you pick these 500 years finishing in the year 2000, and you pick up the color, it is showing when the warmest summers occur in Europe, okay? And the height of the bars indicate the anomaly, let's say. If you introduce the last 10 or the first 10 years of the 21st century, you see a huge change in color and altitude of the bars. And of course, all of these is due to the 2003 heat wave. All of these here in Greece and Turkey to the 2007, and here to the 2010. And while this is great, I must tell you that the last 10 years have changed this dramatically. I have no time to show you, but basically in the last 10 years, most of these is now red again. Okay, we're still computing stuff, but basically all the warmest summers in the last 520 years are happening in the last 20. Basically, okay? For those of you that don't like to mix good observed data with proxy data, this is the same graphic, just with observed data until 1880, and you can see basically the same. The first 10 years of the 21st century changed dramatically this picture just by changing here 2000 to 2010. So, what was the impact of these 2 major heat waves in net primary production in Europe? Well, if we look into Western Europe, of course, 2003 implies a major drop. while in Eastern Europe, 2010 is the real king of all drops in net primary production. So this is for this part, and this is for this part. And we compare that with the typical cycle of net primary production for the amount of years we had at the time, I don't remember. And we can see here the months where this drop was particularly significant in each of these heat waves. And we're doing that on a regular basis for all these major heat waves. So finally, what is happening in the last few years? In the last few years, we are observing an acceleration of all these processes. So 2017, unfortunately, Portugal suffered a fire season that was even worse than 2003 and 2005. Why? Well, all of these burn. Please bear in mind that in Portugal, it's not the hottest places that burn. The hottest places are here. It burns in places that are not fuel limited. We have lots of vegetation north of the river Tagus, and that is a very important issue. Many people, even in Portugal, are not totally aware. They keep asking why Portugal burns. Well, Portugal burns because we have lots of vegetation, and this is a mixture of Mediterranean type of climate with Atlantic type of climate, in fact. And so there's a big difference in vegetation in the northern part and the southern part, and we have lots of fuel in the northern part. Right, each color represents a different month, and what is amazing here is that the catastrophe we had took place before the season, fire season, the official one, which is July, August, and September. So we had 65 deaths during this week, and we had another 50 deaths just during 2 days in October. So prior and after the fire season, we had these major heat waves that killed lots of people, okay? And let me remind you that in the following year, Greece had something similar with about 100 extra people dying. So let's see what happened specifically in those two situations, June and October. In June, we had a major heat wave, but striking only Iberia and southern France, with record temperatures at the global Iberian scale, particularly for June. And how do we see that? Well, I have here all the anomalies at the 7-day scale. So let's see all the weekly anomalies for June, July, and August. And if you, well, the colors are not the best ones, but June is in red, and all the anomalies are shown here. The line is representing what happened during that week where we had the fires in Portugal, okay? So really outside the distribution for 70 years of weekly anomalies. The blue and green that we cannot see very well are the same for July and August. And what you can see is that this incredible week during June in 2017 was very similar to the hottest weeks in Iberia for July and August, when it's really the peak of summer. This is something also that is a typical implication of climate change. The summer is enlarging, okay? So June is becoming similar to the rest of the summer. And think about what happened this year again. We had major heat waves in all of Europe in June and beginning of July, okay? So this was for middle June and October. What was happening in October when during those, in fact it's not 2 days, it's 1 day and a half, we had the fastest rates of burning area in all the world. So this is faster than the fastest fires in California or Chile or Australia. The fastest rates occur during 16 and 17 of October here. So why? Well, we had the temperatures were high, but the Palmer drought index or any drought index, let me show you. Remember 2004 and 5, was a major drought, yes. It reached 100% of the territory. 2011, 2012 that I mentioned before, again, it reached all the territory in the two most important classes. In 2017, we had, in June, when we had the first fires, 80% of the territory was under drought. In October, 100%. So it was hot, it was extremely dry, and then we had the third component, not very usual, which was a tropical storm passing close to the coast. So of course, this was one of the main dynamical reasons for having these very fast burning rates. But what is really important here for you the takeaway message is all of these three components are being changed, induced, increased by climate change. Dryness, heat wave, and the possibility of cyclones, tropical cyclones, close at these latitudes. Of course, these tropical cyclones, when they travel really fast, and when they reach our latitudes, they quickly change to extratropical, and they lose this high and this very perfect symmetrical shape. But that's not the relevant thing. The relevant thing is that in the last 2 years, we had 2 tropical cyclones striking Portugal. One was responsible for this, and exactly 1 year after, 2018, during the same days, October, we had a tropical cyclone striking Portugal, really, with winds up to 200 kilometers per hour. Okay? And prior to that, the number of tropical cyclones is really ridiculously low, let's say. So this is changing fast, and we know from our colleagues in the United States where this is really a problem, that the number of tropical cyclones is increasing in northern latitudes, which is a big problem for them, but apparently it can be also a problem for us. Right, and to finalize, what happened last year? Well, last year, first let me show, we like to use a dynamical way of defining what is a Saharan air. We use some objective measure, and we can enclose these in this isoline. At the beginning of August 2018, we had a huge heat wave striking only Western Iberia and Portugal with this intrusion of Saharan air. This was exactly 1 year ago, at the beginning of August, but it was sufficient to break all the records in Portugal. And for you to have an idea, Lisbon, the previous record was 42 degrees in the last 150 years, and it became 44 degrees. This was 1 year ago. And when we were writing a paper on this, just one month, last month, we had this major heat wave striking France, and the record temperature in France changed from 44.1 that was observed in 2003, heat wave, to 45.9, close to Montpellier. I don't know if this, Wolfgang, is this official, this record?
Yes.
Yeah. So this is a huge increment, similar to the one in Portugal, so about 2 degrees in just one go. This is not typical of new records. Typically, new records are half a degree, something like that, not 2 degrees, particularly in long records. Right, and going back to the figure I've shown you just half an hour ago, when we were looking at 2003, 2010 heat waves, let's see how these has changed. Well, 2016, that was not there before. 2003 is here, 2010 and 2018. And I would almost bet that 2019 will follow somewhere close. It could be above even, because we had already 2 heat waves. So, not sure, it depends on many other factors, how August will develop. But it will never be too far away from these 2 here. So this really shows how things are moving really fast, and how this tendency for heat waves is happening at a faster pace than we thought just a few years ago. Okay? To be honest, I'm really impressed with what is happening. Not only at the global scale, we had 2014, the hottest year ever by a small margin. A year after, again, a record at the global scale, and 2016, a huge record at the global scale. And in Europe, we're seeing this on an annual basis. So I never thought that we could see climate change happening in real time in front of us, but that is what is happening, basically. Right, so some takeaway message. The Mediterranean climate regions, all of them, are getting drier, and drought frequency is bound to increase during the current century. Recent mega heat waves in Europe, such as 2003, 10, and 2019, have been outstanding, not just at the weekly, but monthly and seasonal scales. This is why they then appear when we compute the entire season. There is a growing tendency for complex compounding events in all Mediterranean climate regions. Let me call your attention, there's a cost action that is starting now with compounded events, and that is mixing particularly drought, heat waves and fires, but also storms, floods, and all of those are really important for ecosystems. All of these, because we cannot compute return periods just for one, but we must take into account the simultaneous occurrence of both. So when you're looking at the effects of heat waves or droughts into ecosystems functioning, you must take into account that you should not evaluate those independently, but also when things occur simultaneously, because the return period might be less than what you think when you put those together. And most regional climate models predict more intense heat waves and drought episodes for the Mediterranean basin, but also for the other Mediterranean climate regions. And that's it. Thank you.
Thank you for presenting this very unpleasant climatic panorama of the Mediterranean world and the surroundings. So, questions, please.
Thank you for your nice talk, a little bit terrifying.
Oh.
Although we feel that the climate is changing, is really amazing to see this supported by some models. As a person that is working in ecology, I would like to know what we can do based on these, not scenarios, but what is happening all over the world. What can we do as ecologists? Can we do something to mitigate these effects, or we just be here looking to this terrifying movie and waiting for a better future? Thank you.
First of all, it's not my intention to provide terrifying message. Things are the way things are. To put this in a broader context, I would probably believe that there are other issues currently that are probably more important than climate change at the shorter time scales, such as plastics in the ocean and the collapse of some insects and some other stuff that is happening at a very fast rate. So at the time scale of a few decades, climate change is really, really impressive. But despite this, I believe that we have some capacity to adapt. I'm not entirely sure, and probably because I'm a physicist, that we are capable of adapting to the amount of plastic that we are eating in the short term. So to put things in a perspective, probably there are other issues happening currently that are as important, at least. But to be honest, I don't think there is much we can do. We can influence the amount of greenhouse gases that we're going to put into the atmosphere in the coming years and decades. Looking at how things move so slowly in the last few years, for example, in 2015-16, there was apparently a drop or a stabilization of the amount of new CO2 into the atmosphere, but that has increased in the last 2-3 years. the capacity we have to change that, where at the same time we have all these people in China, in India, that are trying to obtain same level of life that we have in Western Europe and States and other countries, it's very difficult to change. So I'm not very optimistic in the way we can, unless there is something providing a new discovery like fusion, electricity, and I'm not sure that we can change these in the short term, unfortunately.
Yeah, thank you, Ricardo. It was a very good talk. I would like to argue a little bit about the forest fire that I know you've worked on in a number of papers, and of course nobody questions the importance and the intensity of the recent forest fires, but the attribution of them is a very complex case for every one of them. Right? For example, the decline of agropastoralism in all of the Mediterranean is basically the reason why there is so much vegetation out there.
That is the basic reason.
Right, and then there are additional things. For example, the French army a few years ago, they performed a lot of testing with I don't know, some new sorts of missiles in the driest season, and they created a big forest fire from that. In southern France, I'm told by the experts that 9 out of 10 forest fires are lit either by firefighters themselves in a criminal action or by accident from people throwing away cigarettes in places and times where this shouldn't be. So, I mean, the system is out of stability from an ecological point of view, and the additional stress that comes on it from the drought and from the heat that you describe is important, but how important is it? How big is the role of climate change in the increase of forest fires in the Mediterranean?
Definitely what you're saying about the decline of usage of the forest and the decline of the population. That in Portugal took place a little bit after what happened in southern France, Italy, and that is really the major driving force. And again, most of the fires that have been studied in Portugal are related with human action. The fraction due to arson and to negligence changes over time, and even the definition of negligence, it's not totally clear. For example, power lines that we know vegetation should be cut every few years underneath. If they don't do it, is negligence or arson? The definition is changing because some of the people responsible for that in Portugal are going to trial now for some of the fires in the last few years. So, but basically 90 to 95 or even more are due to human action. One thing very different is the perspective from, let's say, a geographer, which is how do you explain the fires where they are happening? From that perspective, human occupation, roads, electric power lines, all of that are the main predictors that explain especially up to 95% of the variance. That has been studied for Portugal and it's similar to other. Now what we're talking about is temporal variability. If you're talking about temporal variability, you must think of, in Portugal you have thousands of people producing fires every day. A few of them are arson, but I would say that the majority is negligence. Stochastically, you have people doing bad things all over. But why do you see some of these fires, like we had last week, that grow out of control? That is mostly due to climate. From that perspective, if you have a higher frequency of heat waves together with dryness, then that increases the burn area associated.
So with respect to your last answer and the answer to the first question, this is a naive meteorological question, which is, at what temporal scale are we able to predict the arrival of these mega heat waves? Because if at least we have a little bit of head start time, we can put in mitigation measures, you know, for example, banning people from going in certain areas and taking cigarette lighters and things with them and all that kind of stuff.
Mega heat waves, you can predict them correctly with a week, which is quite good nowadays. But it's also important, and we're doing that with companies here and with National Civil Protection here, because fires here are so dependent on the amount of rainfall in winter and the climate conditions during spring. When we reach the beginning of June, in our group, we can provide a forecast tool of what is going to be this coming year. If it's going to be above the average, below the average, what are the probabilities of that happening? For example, in 2017, we were in a meeting with a company that is paying us some of this stuff, and we told them on the 5th of June, this is going to be a really above year in terms of burn area, and was. And in 2018, that was probably even more interesting, because it rained a lot during spring. We knew that even with a heat wave that could occur, it was going to be a year below average. And so that was the kind of forecast we provide, long-term forecast. And we had the strongest heat wave, as I mentioned, at the beginning of August 2018. And in the middle of that heat wave, one of my colleagues was on TV saying it's going to be a year below average. Because we knew that fires on the average, the total burn area in Portugal depends a lot on these compounding effects of spring together with the heat waves. And because spring pushed everything so much lower, even with a heat wave, things would be lower. But that was a tricky one, and we had a major fire in Algarve. But in 2017, we had more than 500,000 hectares, and in 2018, we had 40,000 hectares.
Thank you very much. You said at the end of your talk that you were surprised to see climate change happening live. That's a strong statement from, I'm sure you're not the only climate specialist to say that.
And the type of statement that I would never say 5 years ago.
Yeah. What are the technical aspects or reasons that you think, from your point of view, that we missed 5 or even more years ago, and that we did not see, and that comes to this conclusion?
Several. One is that when you look into distribution, the changes in the average of 50 percentile go slower than the 70 percentile, the 90 percentile, and the 99 percentile. So in these typical changes of temperature distribution, as I've shown before, the changes in the 99 percentile are much faster than the other ones. And the capacity to attribute that to climate change is really much higher than some of the others. So when 20 years ago we were looking into changes that are compatible with what we've seen in the Mediterranean regions, we did not realize at the time that changes, we knew that extremes were different, but we didn't realize that changes would be really faster than on the average. That's one thing. The other thing, more structural, was, you know, that during a period of 10 years, the first 10 years of the 21st century, the global temperature didn't rise that much. So we had the El Nino in 98, and then only in 2014, 15, and 16, temperature got up to the same rise that it was going before that hiatus in climate change. The reason for that apparent hiatus, that is not a hiatus at all, when we look into the last 60 years, it's you can see a straight line going up. The reason for that apparent hiatus was a huge amount of energy that is going into deep ocean. And the capacity of dynamical models to model and incorporate those components, it's not just El Nino, it's other stuff that is happening at slower scales and is putting most of the energy into deep ocean, okay? And that means that 20 years ago, models were not good enough to include those components, and nowadays they are. So models now can reproduce that type of variability, and they can reproduce that apparent lack of increment of temperature. But 20 years ago, they were not able. So things are improving both from the dynamical perspective and from the statistical one.
And very last quick question from you.
Thank you for this opportunity. Very quickly, from a practical perspective and applied ecological perspective, I'm busy with a very large restoration project in the area that burnt in Algarve, in the Montchique area. We are trying to recover natural habitats. My question to you is quite succinct, because we're dealing in a small contextual aspect, and a lot of the science we have is very global and regional, and it doesn't apply. It's very difficult to apply it into a small context. So I'm working with Miguel Araujo and his team, and trying to understand how we apply what you guys are finding out for us who are putting the vegetation back in the ground, from the fire aspect, and understanding all the other contributing factors, the drivers, because we've got lots of land degradation in this area. And trying to understand how because we are looking into the future, we're putting something in the ground that's going to be there for 20, 30 years. And how do we apply the concepts of reference or novel ecosystems, because we don't have anything to go on. The 2003 fires destroyed everything. They hasn't recovered, because what has happened is the change in land use has been more to monoculture than back into the original vegetation. So people took the opportunity. My land burnt, let me just plant eucalyptus. So we have a river basin that is a Natura 2000 area, 90% under the classification, that has 46% eucalyptus in it. The eucalyptus burnt.
But it was burned in 2018?
2018, and I'm doing research in that area at the moment. It hasn't returned. There's been very little regrowth in that area. And so we are going in to do assisted recovery, but we're stuck with one of the difficulties of how do we do assisted recovery and take into consideration all the other driving factors that are coming into play. And of course, sitting at a table, everybody has a different opinion. And I would like to understand, obviously working with Miguel and Diogo Alagador, and various other people, we are trying to take the theory and put it into practice. And so my question here is, how do we create this link when we're dealing very much from a global or a regional perspective on climate change, and suddenly we have local contexts where we come down to hectares and not thousands of hectares of areas, and specifically in little areas like this river basin, which has an Atlantic influence, has big mountains, 900 meters on the landward side, and slopes that are over 42 degrees in aspect, as well as north-south, east-west aspects. So from an ecological perspective, it becomes very difficult to try and model or design recovery processes.
That's very easy to answer. I really have no idea.
Good. Thank you very much.
Okay. Thank you very much, Ricardo. Thank you everybody for being here and for contributing to this session. Thank you.